The pictures we are going to see today are slides from the type course. So they've been carefully picked out to marry the information you've got in your notes and also provide some detailed information about the overall system. First picture is the component location of everything to do with chapter 24. We have two engines and two IDGs. They're called integrated drive generators. We'll touch on that later on, what an integrated drive generator is and not just a straight generator. Each IDG produces 90 kVA. It's capable of 90 kVA of delivery power. We have an APU starter generator. So it's a starter. And then it converts to a generator once the starting of it is finished, so to speak. That also produces a 90 kVA up to 32,000 feet. And then it progressively reduces down to 66 kVA at 41,000 feet. We also have a fourth AC power possibility, which is the external power, which is a plug-in ground power unit, also capable of producing 90 kVA. We say 90 kVA, it's all three-phase, 200 volts frequency wired, so it's really strong system. I mean, you could light up a small city with one of these generators. You're talking 200 volts AC, a three-phase, it comes down to 115 volts at 400 hertz when it's regulated onto the equipment. That's for the AC parts of it. We also have DC power, where we have three transformer rectifier units. So the transformer rectifiers, they transform the AC that's generated from the generators to DC to use on the aircraft, 28 volt DC. We have a main battery with its own charger here in the avionics. And then we have an auxiliary battery with its own charger. So that's for the DC power producing equipment. And then we also have standby power. So with the loss of normal power, the standby power system supplies a minimum of 60 minutes of AC and DC power to the systems necessary to maintain safe flight. 60 minutes on the batteries, but the batteries only have DC. However, the batteries operate an inverter, and that's all inbuilt in the 60 minutes, and the inverter will invert then the DC back into AC, single phase, to operate some systems, the most necessary systems, in order to maintain aircraft power for minimum of 60 minutes as prescribed by the regulation. Okay, simple system layout. Okay, this is a little description of what the LRUs, the line replaceable units, look like in real life. Okay, so we've got three panels that have to do with the electrical power on the P5. That's the overhead panel. And we have GCU1 generator control unit, okay, which is the brain, so to speak, for the IDG1. GCU2 for the generator, the IDG2 on engine number 2. We have an AGCU, an APU generator control unit for the APU. And then we have a bus power control unit for the external power. So all these four possibilities are able to supply the two AC buses here via these two very important, what they call bus tie breakers. The bus tie breakers is a very important system on an aircraft, even when they designed it in the 50s. So the idea of the bus tie breakers is that you can have one generation system supplying all the buses you want, but you can never have one bus being supplied at the same time from two generation systems. That's not possible. It's not allowed. If it happens, you'll get the big boom. Yeah? So that's why we have the bus tie breakers, and they're sort of mechanically connected so that You can never have one bus being supplied by two generation systems at the same time. So we've got the 4 generation systems for AC. They get to here, to the buses, and then the bus AC goes to the transformer rectifier units. And the transformer rectifier units then transform the AC, the on-side AC, into DC for use for other systems. Okay, the AC also supplies the 2 chargers, the main and the auxiliary, and the main and the auxiliary chargers charge constantly the battery. So that's a general layout of the system and what the boxes look like. In our world, we call them black boxes because invariably they're all black boxes. Even the CVR and the FDR, which is an orange box, we call a black box because they're all black. They're all black, and inherently we just call them black boxes as an abbreviation for a computer for its name that's this long. Sometimes we just call them black boxes. This is what they look like, and they are constructed in a certain format with certain dimensions, so that various different vendors can manufacture these things. It's an ARINC spec, so that if you want to start building transformer rectifier units, you can, as long as all your electronics fit in these dimensions and the back plug fit onto the existing aircraft. We also have a possibility, other than these 3 panels, a 4th possibility of switching the ground service power supply is strategically located after the cockpit door on the forward attendant panel, as we said, so that it enables unqualified staff like cleaning crew, for example, they don't have to go into the cockpit to put the power on and maybe switch something wrong on. So it's kept out of the cockpit, and it's on the forward attendant panel to enable them to switch the ground service, which will give them power, the AC power outlets, the cabin lighting, so that they can clean the cabin, the lavatories, so that they can clean the lavatories, and the power sockets near the doors to be able to plug in their vacuum cleaners to be able to vacuum the carpets. Okay, so the first one of our 3 main boxes, this is called, I'm sorry for this, but that's how Boeing made it, and that's how they called it, the Electrical Meters Battery Galley Power Module. Okay, they couldn't make it longer if they tried. It's a bit of a mouthful. If you're thinking we've got an emergency, explain the problem as quickly and concisely as possible. Oh, switch on that switch on the electrical meters battery and galley power module. Oh my God, we crashed already. Yeah, they couldn't give it an acronym or something small. The name is this long, and we live with it. So this unit enables us to check the sources and the voltages and the general health of the electrical system. It also stores faults in the electrical system for the engineer to have a look at after the flight. The second panel is called the Generator Drive and Standby Power Module. And just like the name suggests, it evolves its life around standby power and the generator drives. Okay, so these are the IDG disconnect switches. Notice the red capped switches. To disconnect the IDG, operating those switches with the red caps has irreversible consequences. Means once you've disconnected the IDG, okay, so the IDG, it's a spline, and it's turning inside the engine gearbox. Okay, when you disconnect the IDG, it means you pull that spline out, okay, and the IDG is no longer rotating. But you cannot reconnect the IDG. Once you've disconnected it, you have committed an irreversible act. Okay, so that's why they're painted red, so that when you go to operate it, it's like the fire handle, the fire switches. They're not red because of emergencies. They're red because once you shot the bottle, that's it. You've got no more bottle to shoot. So make sure it's a real fire before you shoot the bottle. Okay, it's the same here. Make sure the IDG is really bad before you disconnect it, because if you it's different from the generator switch. The generator switch you can have on and off, the bus on, off, as many times as you like. But the IDG, to mechanically disconnect it, one time only. Okay? So get that clear in your head. All the red switches are one time only. Then we have a few indicators operations for the standby power, which constitutes, the standby power constitutes the AC standby bus, the DC standby bus, and the battery bus. The third panel we want to talk about is the AC systems, generator, and APU module. These are the ones, see, they're the bus, generator, on, off, no red. You can switch a generator on, off, as many times as you like. But if you disconnect it, that's it. All right, so we have two switches for the APU. Still to this day, you only need one. There's only one generator supplying the buses, but they've duplicated them. Still don't know why. Operating one of these two, okay, we'll put the APU generator online and supply AC main bus 1 and main bus 2. I don't know why this design is like that, but the overall idea is that you have, each generator has its switching system, and through the bus tie breakers, all these, plus this one, okay, from the GPUs, another 815 volts power source. All of these work in cooperation with each other with these bus tie breakers. So if you switch the ground power on, and then you supply them with the ground power, and then you run the APU and put the APU generator on, it will switch off the ground power. You can't have ground power and APU supplying at the same time. All right, so these switches give the pilot control over which bus they want supply, and invariably they switch this on for the duration of the flight. And generator 1 is invariably supplying the main bus 1, and generator 2 is supplying main bus 2, and the APU is switched off in flight, and the GPU is not connected in flight. So invariably the two generators are enough for a safe flight from A to B. If at any situation one of the generator fails in flight, the pilots can start the APU and use the APU generator as the second source. Okay, the second generator, which will supply as the second source to the buses as required. And the bus tie breakers will click and switch in accordance with what is required, so that each bus will get supplied by one source.